First speaker is Yoshinori Matsuo. He's from NTU, and then he will tell about the black hole and the white light transfer.
Thank you. Today I will talk about this my recent work. This talk is based on these works. This is about black holes and black hole information loss paradox. Black hole evaporation appears because if we consider gravitational collapse, then because black hole is formed by gravitational collapse, but if we consider quantum vector in gravitational collapse, there is a Hawking radiation. If black hole is its energy by Hawking radiation, then black hole finally evaporate. The problem of information loss is that if we consider classical black hole geometry, then information cannot get out from the horizon of this black hole, but quantum theory means that information should not be lost in this quantum theory. There is a contradiction from these two pictures. That is a problem of this information loss paradox. In order to consider this information loss paradox, we would like to consider quantum vector in how this quantum vector affects this black hole geometry. We consider this semi-classical Einstein equation. Here we consider Einstein equation, but here in energy moment tensor we consider the effect of quantum energy moment tensor. This is a quantum vector in matter field. If we this is a conventional picture of black hole evaporation. If there is a gravitational collapse, then we compare this vacuum state with that after the gravitational collapse. This vacuum state evolution of this vacuum state is along this new line, and because of gravitational collapse, this is just vacuum state, but after the gravitational collapse, there is some Hawking radiation. But this Hawking radiation always appears in the causal path of this event horizon. This event horizon is not important for this Hawking radiation. Only if there is a gravitational collapse, then there is a Hawking radiation. And if this matter is almost behaves like a black hole, then there is a Hawking radiation. Then, from the viewpoint of reducer observer, gravitational collapse of matter can be described by this picture. This is a time direction, and this is a radial direction. And matter is approaching to this Schwarzschild radius, but when these matters get inside of this Schwarzschild radius, then there is a horizon appears in this geometry, but actually, it takes infinitely long time from the viewpoint of reducer observer. The observer saying outside. But if this black hole evaporated in finite time, then this evaporation must happen before these matters get inside of this Schwarzschild radius. Schwarzschild radius for these matters decreases because of this Hawking radiation, and then this Schwarzschild radius decreases in this way, and collapsing matter going inside and approaching to this event Schwarzschild radius. But before this get inside of this Schwarzschild radius, this finally this matters lose all energy and finally evaporate. In this sense, if this black hole evaporates in finite time, then there are no event horizon in this geometry. But this picture is a bit naive. In conventional picture, there is actually negative energy. Hawking radiation does not directly appear from the collapsing matters, but just appears in the bulk. And then, in order to satisfy the conservation equation for this matter field, there must be some negative energy going inside of this horizon. Black hole, Hawking radiation doesn't directly take this energy from this collapsing matters, but because of this negative energy going inside of the horizon, then because of this negative energy, black hole loses the energy and finally evaporates. This is a computational picture. But this negative energy actually, appears, actually we would like to consider this negative energy. So let me first explain about the model. So we consider the S-wave approximation for this matter field. So we approximate this to calculate this energy momentum tensor. We just consider two-dimensional matter field in time and radial direction, and we just integrate this angular direction. And for two-dimensional scalar field, this energy momentum tensor can be calculated by using the Weyl anomaly and conservation equation. So this comes from the Weyl anomaly. So Weyl anomaly completed this diagonal components, and trace part of this energy momentum tensor. And then by integrating this conservation equation, this energy momentum tensor is basically fixed, completely fixed. But there is also some integration constant because we are integrating this conservation equation. And actually, so this part that comes from Weyl anomaly is actually independent. Weyl anomaly is independent from the physical state. So this is this part is independent of physical state. That is something like Kashmir effect. And this negative energy of in this black hole spacetime can be considered something similar to Kashmir effect. And this integration constant actually related to the physical state. So this integration constant actually describes the physical excitation of matter fields. But if we consider the vacuum state, then this energy momentum should be zero in flat space. So we choose these constants such that there are no energy momentum tensor in asymptotically flat region. Then in that case, this negative energy also appears even in static configuration. So if we consider impose the condition that energy momentum tensor is zero in asymptotically flat region, then time evaluation of this state, vacuum state, gives negative energy inside of this geometry if there is some star. And actually, so this picture have no problem if there are no horizon. So for ordinary star, this just means that there is some quantum negative energy in the back. But if there is an event horizon, then this negative energy actually diverges at the horizon. So usually this vacuum state, this condition is considered as a physical condition. So people usually do not consider this so-called Borel vacuum, but we will consider the back reaction from this energy momentum tensor to the geometry, and then we found that there are no divergence of energy momentum tensor even at inside, even if there is even for the black hole. So actually, so this divergence we can from the viewpoint of fiducial observer, actually we do not see any. In some sense, this is not very defined, but we do not see divergence. But for freely falling observers, and this negative energy is infinitely large, so this is a divergence of this negative energy at the horizon. But in order to satisfy this semi-classical Einstein equation, so if this diverges, this geometry must also diverge. But usually at the horizon, this curvature does not diverge. So in order to satisfy this semi-classical Einstein equation, this geometry is also modified such that there are no divergence in vacuum energy. Then actually we calculate this the solution of this that semi-classical Einstein equation and find that actually there are no divergence around the Schwarzschild radius, but geometry is modified like this kind of wormhole. So around the Schwarzschild radius, the actually R is decreasing as it approaches to the supersolids radius, but after it gets inside of the supersolids radius, R starts to increase as it goes inside. So this looks like something like a wormhole. But actually, so this wormhole is not continuing to asymptotically space, but this just I just means there is some local minimum of this radius. And this picture can also be understood from the perturbative expansion. So classical solution, this I choose another coordinate in radial direction, and this is some sort of proper radial coordinate, and this radius R is actually radius of two sphere in the black hole geometry. So this radius is approaches to the supersolids radius at this here is a horizon in classical geometry. And if we consider perturbative expansion and this classical solution, we found that the quantum collection becomes very large at the horizon. And actually, this R quantum collection, quantum collection is this one. So this diverges around the horizon, and this is actually solution for R. So classical solution dominates and asymptotic region, but near the supersolids radius, quantum collection becomes important, and R starts to increase again. So R goes infinity at the horizon again. So this is
so in 4 dimension, the quantum fluctuation is also negative.
fluctuation.
If you have T mu wave, right? In 2 dimension, due to a number, is negative. In 4 dimension, is it positive or negative?
We are considering just how to say
In 2 dimension, it's negative. Right? This part due to a number.
this one.
Yeah. But in 4 dimension, you later consider 4 dimension. You have also T mu wave. Is that positive or negative after subtract the UV divergence?
Actually, that depends on the. So it depends on the model, and so we are considering the case if there is a negative energy in energy momentum tensor. And so this is just not just a 2-dimensional energy momentum tensor, but this is just S-wave approximation. So this is just we are considering the mode with zero angular momentum. Then we found there is negative energy. And if there are no negative energy, as I explained before, there are no.
So in 4 dimension, you have dimension reduced due to spherical symmetry in 2 dimension.
Yes.
So this argument also goes through.
Yes.
But if I don't have spherical symmetry,
in that case, we have to consider also the effect, but we do not consider that effect. So, okay. So, in this sense, we found this wormhole-like geometry, but there is another singularity at there is a singularity at the center of this geometry, and that is at the another R to infinity limit of in the other side of this hole. But actually, this singularity appears because we are considering vacuum solution. There, matter configuration. In this matter configuration, there are no excitation from the vacuum state. So if there are no vacuum state and no matter excitation, then there is nothing to give mass of this black hole. So there must be some singularity for this mass. Then this singularity should be replaced by some matters with finite distribution. So if we consider matters with finite distribution, then it is naturally expected that there are no singularity, and geometry actually becomes like this one. So we actually checked this picture by using incompressible fluid. So we consider the matter. So matter is diffused somewhere inside of this neck of wormhole. Then we assume that this density is constant inside of this this region. Then we found that this kind of geometry. So there is actually outside of this matter distribution, there is a neck of wormhole-like structure, and then R is increasing inside of neck, but inside of matter distribution, this again goes to 0. So there are no event horizon and no divergence. And actually, so let me just comment on the relation between density and this geometry. So in order to have this kind of geometry, density of the matter must be very large as a Planck scale. So if this density of matter is less than Planck scale, then matters overflow to outside of this Schwarzschild radius. And if this piece is actually density is divergent, if density is infinity, we have one more x. Sorry. And so if we consider time evolution of this metric, then we also found some apparent horizon. So apparent horizon, inside of apparent horizon, this R is decreasing along outgoing and ingoing neurons. But actually inside of this neck, R is decreasing along outgoing lines, but increasing along ingoing neurons. But if we consider Hawking radiation, this neck is also shrinking because of this Hawking radiation, and then R is decreasing both ingoing and outgoing lines. So we have apparent horizon, but this apparent horizon is time-like, so information can get out from the apparent horizon. And we found this structure on constant U slices. So if we consider time evolution, then one possible picture is just neck is only the neck is shrinking, and then finally this inside of this connected from the our universe. And another picture is all this inside. If this all inside of this neck is shrinking, then finally all information can get out from this black hole. But here we do not know which is correct still. So this is our future work. So this is a summary. So if there are no negative energy, then there are no event horizon, and there is no information loss. And if there is negative energy, then static case, there are no horizon and no singularity. And if density is small, then this picture is same to ordinary case. But if density is very large, then geometry has neck. And if we consider dynamical case, there is an apparent horizon, but that does not have any information. And there may be event horizon, but so this is only a speculation. But this event horizon appears because of this neck. So this event horizon appears only possibly appear if density is very large, and if density is not so large as Planck scale, then probably there are no event horizon. That is our conclusion, and we do not know how about in this case. Thank you very much.
Just to make sure, the last page conclusion is based on the suppression of the harmonic. So it's assuming the two-dimensional excitation from the radio movement.
Yes, actually, we are always considering only exterior approximation.
So usually, can I understand why you don't have horizon? Because the Casimir force it cancels the gravitational collapsing. Can I understand this right?
I think that is so. If there is some sort of coordinate singularity at the event horizon, but this vacuum negative energy is not always only the negative energy, but vacuum energy is actually finite from out of this coordinate singularity. Then this means if we consider some good coordinates, there is some singularity. As far as there is finite energy from the viewpoint of fiducial observer. So that means if there is finite energy at the horizon from the fiducial viewpoint of fiducial observer, then this reaction cannot be neglected, and then there are no event horizon is.
But suppose I consider correction share, and I can actually try to calculate the sum of the resonance mode to hold up this whole correction. If I cannot find enough force to hold up this correction, maybe it's finally will still correction become a black hole. In your case, you consider already there's a black hole, and then you have the documentation. Suppose I consider.
No, we do not consider the how to say. So I just mean, for example, if we consider the gravitational collapse, then when this across some point where there must be a horizon, then just outside of this collapsing matter, this negative energy modifies becomes important, and taking this effect into account, there are no event horizon. So even if we consider gravitational collapse, there are no event horizon.
Yeah. Then, but there's possibility.
Maybe you can calculate.
Okay.